Hello again. So I want to talk about the global workflow of DNA data storage. And I think that it's an overview of what we will see during this week, and you will have more technical talk during the week that will be made by specialists of the domain. But I want, just to give an overview of DNA data storage. So let me, okay. So I'm used to start my presentation by this slide. So I like this slide because it is showing the first hard disk drive in the history of computing. And as you can see here, the hard disk drive was built by IBM 70 years ago, and its capacity was 5 megabytes of storage. And the weight of this hard disk drive was 1,000 kilograms. So, as you know, if you take a picture like that of 12 megapixel and JPEG compressed, and you put that on your smartphone, and probably you have, I don't know, thousands of this kind of image in your smartphone, the weight of this image is the same as 5 megabytes. So, as you see, things has evolved, of course, and 70 years ago we could say, oh, using hard disk drive, it's very complicated, it's heavy, and I don't care. And maybe you are saying, or people are saying that today about DNA storage. It's too complicated, it's too slow, and it's too expensive. 1,000 euros for 1 megabyte. At that time, it was $10,000 per megabyte. So $10,000 at that time. So it's much more than today. So it gives us some kind of hope for DNA storage, and assuming that in some years, and maybe faster than 70 years, we will use the DNA storage as a DNA media. So probably you know, 1 single graph of DNA, it's 215 petabytes of data, so it's theoretical. So it's very compact. It has also the property to last hundreds of thousands of years. Of course, if you keep it in good condition, so it's cool or dry place. And it's an eco-friendly solution because once you synthesize the DNA, you don't have to spend any energy to store it. If you store it in specific capsules, for example, or in good place, you can keep it at room temperature for a very long time, so you don't spend any energy consumption. So as we said, as I said previously, so the bottleneck is speed in synthesis and in the speed of writing. Of course, people will say also that one of the cons is high price, but this is the false problem because I think that most people will use DNA for storing information, and the more the price will decrease. Anyway, my compression normally is focused on my talk is normally focused on compression, and what I want also to show here is that compression is not optional, but it's fundamental. So even if you are able to store a lot of data anyway, you will face two problems: the writing speed and the cost. So you don't want to do a lot of time for writing your information, and you want to pay a lot. So at the end, you will be able to compress your information, even if you have a lot of space for storing it. Because also, as you see here on the curve, the quantity of information is growing exponentially. So anyway, we will produce maybe more data than we will be able to write it on DNA. Okay, so DNA, I think that you will see a lot of talk this week talking about that and about DNA, and probably Pascal will talk about that. But I just want to show here that we are considering the 4 bases or the 4 molecules of DNA as an alphabet for being able to construct code. So it's my, let's say, computer science point of view. I use ATCNG as a dictionary, or a dictionary of symbols for building efficient code words for writing on DNA. What is important also is that also some people are asking this question is, well, you are manipulating DNA, so DNA is life, so what happened? There are some ethics questions, and what I want to say here is that we are not building DNA that contain life or any codon that allows to produce life, and especially because we are just converting bits into quaternary and alphabet into quaternary code, and it's not the probability even to generate such kind of material is very low. One also importance of using DNA is the DNA is an unchanged formula for 4 billion of years. So it means that if life exists in several years and we have the capacity to read DNA, probably we will be able to read molecules and to read the information, maybe not decode, but at least to read the information stored on DNA, which is not the case with this, because maybe some of you know the tape VHS Betamax, or it's very old, so maybe you have this at home, and you are not able to read back this tape because you don't have the device, in French, magnétoscope, you can use for reading back the information. The same, maybe CD-ROM and DVD, so on Blu-ray, so people are using this. Now you prefer maybe streaming data instead of using such kind of device. And also, so maybe in one day you will not be able to read back what is written in CD. And also here, it's a LTO, for example. This is the way people are storing information in data center. It's a small tape like that. So it's the last generation can store 10 terabytes of information in one tape. And this is evolving continuously. So it means that there is new generation of tape that appears, and maybe you will not be able to read back. You will not have the device, and so you have to change the device for reading back or writing information, such kind of tape. And also, since the tape is you change the tape regularly because the format is changing, and also because this kind of medium has a short duration, life duration. I mean, if you take a hard disk drive, it's 5 or 10 years, or if you take a tape, it's around 20 years. So you know that probably your hard disk drive in 5 years will not work. So what data center is doing continuously, they are migrating their information on new device, on new generation, or even on new device, because they know that the device, that the hard disk drive, for example, will maybe crash one day, so they don't want that, so they are migrating information constantly. And so this, of course, produce high energy consumption. So let's say the data center today are consuming a lot of energy because mainly of data migration, which is not the case, which is not used for DNA. When you are storing DNA, you know it's very redundant, so you don't need that. You know that it's very stable a long time. But if you want to do migration, or if you want to duplicate your information, you can by doing some PCR amplification of your molecules, and you can amplify and have a lot of you can store a lot of copy of what you have without a strong energy consumption. So the timeline, something interesting in DNA storage is, the timeline that probably it's not, we know that probably that we don't have really for hard disk drive storage or tape storage, is that the idea of storing data on DNA is we have two ideas: storing data with an eco-friendly solution, and it's also storing data for long-term archiving. And so we can define the near future, the medium future, the archaeological future, and the paleontological future. So the near future, it's 10, 20 years. So let's say it's when you want to store data for DNA, it's a short time, but it's still it's long time anyway, 10 or 20 years, or even 50 years. And probably you know that some legal document must be stored for a long time. So I don't know, for lawyers or things like that, you must store 50 years or 20 or 50 years. Medical data also, it's 20 years. So you have to store for a long term. So you know that it's this is the cold data, what we call cold data, and you store it. Probably you never read back this information, but you know that you have it, and if one day you have to read it back, you can. So this is what we call the near future, and in that case, we must be able to. From my point of view, it will be some kind of hybrid solution. So with part of information stored in binary and all part in quaternary, so in molecules, and you will have to switch between these two information, and mainly meta information will be kept probably in binary to be able to recover your quaternary information. But this is okay. This is okay because we know that it's a short-term storage. So we know that we will be able to recover this meta information. If we want to go for a longer time, so more than 20 and around 100 years, and even I think for 10, 20 years, of course, we have to develop a standard for decoding the information on DNA, and the standard for the algorithms for being able one day to, if you want to decode, to be able to re-encode your algorithm to be able to read back your data. Okay, you do sequencing, but once you have the molecules, sequenced molecules, so you have a quaternary code, and you want to do error correction, to do post-processing, and then to come back from DNA, the quaternary code, to binary information. And this is the way you encoded your data, your binary data into quaternary. So you must know how the decoder is working. And this is a matter of standardization. And of course, at that moment, we should have standards and strong standards to be able to decode information. And also we will be able to encode in some way how the standard is working for future generation. Because you don't know that if a JPEG standard in 50 years, probably you will not be able to decode it because you lose the way it works, and you are not able to implement it again. We don't know in 50 years what will happen. So some people are working on that, how to preserve this information for future generation, being able with the knowledge that we have at that moment to reproduce the algorithm that encoded the data, or at least reproduce the decoder. And then we have for the future 1,000 years, and in that case, probably we have to define correctly protocols for reading DNA. How all the, let's say, the biochemical process for being able to retrieve information from the molecules. And then if we are talking about more than 1,000 years, of course, everything should be taken into consideration, of course, and here we should take into consideration the standardization. But at that moment, something very important is that we must be able to identify that DNA sample is not natural and it's not carrying life. And so people that will do sequencing of that must be sure that, must know that this is not life, but this is binary information that was stored. So the global workflow when we are doing DNA storage is the following. So we have, I put an example as image, but you can store whatever you want. So it's just an example here. So you have encoder part and decoder part. So encoder, it's how to encode information from binary to quaternary. And then, and of course, it's not obvious, and we will see that in some courses in the school. So we have to take into consideration constraints that are imposed by the biochemical process, and also develop some kind of error correction code for being able to take into consideration also the noise that is introduced in the biochemical process. And then, once you decode this, since you have noise here, you must do error correction, post-processing error correction, and then finally decode the information. And according to the information you encoded, maybe you can tolerate some errors or not. If I'm decoding images, maybe I can accept some noise or artifact in the image because they are not visually, or they are visually acceptable. If you are decoding a binary file like PDF or others, you cannot accept an error in 1 bit because you will not be able to decode. So the process here is strongly dependent on the data that you want to encode. And in the middle, there is a biochemical process, so the synthesis, storage, and sequencing, so writing, reading, and storage. And we know that all of this is introducing noise. Today, we are focusing mainly on sequencing noise because we are using, if you are ordering oligos in companies that are synthesizing such kind of information, you know that the synthesis is almost perfect, so there is no noise or a small quantity of noise. So you know that when you have error when you are decoding your information, this error is coming from the sequencing. But in the future, and especially with what we are doing in MoleculArXiv, accelerating the synthesis will also introduce noise here. So we will be able to tackle this noise and to do some to work on modelization of synthesis and sequencing noise to be able to design good error correction. And of course, storage. We assume that today storage is perfect, but probably there will be storage degradation, and we should be able to also to model this and to take that in the decoding process. So this is mainly the workflow, and in this school you will have several courses on the different part of this workflow, and also with industrial point of view. So normally it's a very complete, let's say, school. So I have some video here, but I will not show you this video. It's for synthesis and sequencing, and I think that you will have the opportunity to see that later in the school. I want just to talk about rapidly about the noise introduced by the biochemical process, and there is mainly two kinds of noise, so substitution noise and inverse. So substitution noise, letters are changed by others, so you keep the length of your DNA molecules, but you are just changing what we call bases or nucleotides. And inverse can be split in insertion and deletion, so you can have nucleotides that are inserted in your molecule or are deleted from your molecule, so then it changes the length of the molecules. Okay, so we have to deal with such kind of noise when we want to do encoding and error correction for DNA storage. And something important is impact of this noise on the data, and especially here I show some example on an image because it's visually, so it's interesting to see that. And there is three kind of algorithm here that are used for encoding the information. This is, let's say, the trivial algorithm, which you take a JPEG file, for example, in the case of this cat image, and you have a binary file, and you convert this binary file into quaternary. So if you do a deletion in this file, it is what happened, because you are not able to receive. There is no error correction. It's just to see the impact of the noise. So you have no error, resynchronization here. So you are losing everything, which is it's the same example here. Everything after the deletion. And then for these two algorithms, it's a closed loop algorithm. So we encode, instead of encoding in binary and then converting in quaternary, we encode directly in quaternary. And then this is what we can have. It's a JPEG algorithm, and we change in the JPEG algorithm the binary encoder and by a quaternary encoder, and we have some kind of this kind of errors in the image. And finally here it's a specific algorithm where we are using fixed length code and not variable length code, because this is the case of these two algorithms, but this is only fixed length code using vector quantization. And we can see that, of course, since it's fixed length code, it's easier to resynchronize when there is a deletion error. And then we see that we are losing some information here, but in the rest it's correct. So according the way the image is encoded or the data is encoding, the impact of the noise is different. And so we have to consider that also when we are doing encoding. It's what kind of coder, decoder, and what kind of error correction we should use for being able to be robust when we are decoding, because we know that we always have errors in our biochemical process. So we should be able to take into consideration these errors. So there are these errors of substitution and indels, but there are also some coding restrictions that we should consider, and mainly the first one is reducing synthesis error is to synthesize short oligonucleotide. Today it's around 300 nucleotides that we can synthesize with a very low error rate. So this is a constraint because we have to cut our signal to encode in chunks, such each chunk of 300 nucleotides or less, because you have to format the information. You see, it's not only the payload that you are introducing in your nucleotide, in your oligo, sorry, but also meta information, so headers, offsets, primers for being able to do random access or to do PCR. So of course 300 it's a good length, but it's really not enough if you want to scale up. Okay, and then there is also some coding restrictions. So homopolymer runs. So we have to avoid such kind of code. So repetition of A or T or C or G. The GC content must be also balanced with the AT content to avoid some secondary structure and hairpin, for example. Also, sometimes we don't want to have pattern repetition, so we don't have ATC, 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 for example, which is not good for the sequencing. State of the art, it's a rapid state of the art because it's mainly focused on image processing, and I don't want to focus on image processing. But anyway, you know that the first experiment was done by Church in 2012. The idea is older than that. You know that it's Richard Feynman at the end of 50 that talk about storing information or about molecules. And it was in this famous presentation. There is a lot of room at the bottom, I guess. And Church do the first realization of that in 2012, and he stored digital book, black and white images, computer program, and scientific article, and he set the stage for further and more complex research effort. And it was on the first realization, and then there are several works that appear, and especially the first constraint code by Goldman, who take into consideration the results of Church to design the constraint code. And there is also the works of Grass, Blauat, and also Ehrlich, So front-end code and etc. So there are several algorithms that allows to improve the encoding performance to reach the capacity of the channel, which is 2 bits in that it's 2 bits per nucleotide, and also to take into consideration constraints and noise. And then, but most of this, as I told you, most of these algorithms are transcoding, so they take a binary information and they convert it in quaternary information. And in that case, what we can say, okay, it's nice, because if you have already encoded image or data, you can convert in quaternary, but you cannot have any quality cost control during the compression. So you have the quality cost control here, because you minimize the bit stream here and maximize the quality of your decoded data, but here it's just conversion, so you don't control the cost here. And this is important to control the cost here, because this is what you have to pay for storing molecules. So the idea, instead of doing this, is to, and we can, it's not mandatory, but you can do that. You can avoid converting in binary or encoding in binary, but encode directly in quaternary, and maybe have some mechanism to switch between binary and quaternary if you want. And then doing so, you are able to control the code, the length of the code here, and the quality of your encoded signal by optimizing the quality cost trade-off. And so these are some of the work we are developing, and especially in image coding, and we have several activities on that. So what are the challenges in data storage? So first one is very important, is consideration of noise and constraints. So, and especially the noise and the constraint introduced by new chemical processes and sequencing. Because as you know, in the future, if you want to store with at a high speed and have a high speed writing process, we will introduce noise in the synthesis, and we have to be able to define some models for this noise. So I think it's a very important activity. We have also to design error correction for this noise, noise model and noise introduced in the process, robust decoding, and something also that is important probably is to develop a coding solution for synthetic polymers, and in that case we can go beyond 2 bits per base, which is not the case for quaternary. Also, something also very important is you encode your data, you have your data encoded, you probably put in a capsule a data center, but you know that you have billions and billions of molecules encoding for hundreds, millions of files. So one of the main challenge is the big data management. So how to recover my file, or the file I want to read, without sequencing all my molecules. So this is what we call molecular random access, and there are some activity or strong activity on this domain. So for being able to some kind of hybrid solution, binary and quaternary, or binary and molecular. So you have a structured binary database, and you want to structure the same way inside molecules your database. So this is a complex problem, and it's a challenge today. And also automatic solution, because today it's not automatic, so we have to develop things that allows to be able to read automatically, to write automatically, and to read automatically information without any human activity. So I don't want people that open my capsules and you do some wet lab manipulation for being able to recover my information. So I want that being completely fully automatic, and this is one of the challenges also that we have to face. So I have 1 minute. Okay, so I will not explain the standard, but I want to let you know that there is the first international standard for image storage on molecule. So JPEG DNA will be released next year. So it's the scope of JPEG DNA is the creation of a standard for efficient coding of images that considers biochemical constraint and offer robustness to noise introduced by the different stages of the storage process that is based on DNA synthetic polymer. So it's a part one of this standard that will be released next year, and this standard, this part one is not taking into consideration noise, even if it can, but the standard is not considering that. It's just defining the way you are decoding the information. Of course, if you want to introduce error correction, you can, but the standard is not defining the way you are. It's just to give you some informative solution, but it's not defining a standard for robustifying your stream. This will be probably defined in part two of the standard with error resiliency and unequal error protection adapted to image coding. So, so with a requirement, I don't want to develop this. Anyway, I can talk about that with you if you want, if you are interested. So this is the formatting of the oligos. I guess you will see that later in the school. And that's it. I guess it's okay for me. Good. If you have any question. Thank you.